Our solar system is not where we thought it was. In 2020, astronomers remeasured our position in the Milky Way and found we are 2,000 light-years closer to the Galactic Center than every textbook printed in the last 50 years has stated. Not a rounding error, not a minor revision. The map of our own galaxy, the one we have been trusting and building every calculation upon for half a century, is wrong. And if that most basic number was wrong all along, what else about the danger coming from that center have we completely misunderstood? Now, we find out. For as long as humans have pointed telescopes at the sky, we've used light to measure everything. Distance to a star track, how bright it appears versus how bright it actually is, position of a nebula. Follow the wavelengths, map the Milky Way chart, the visible glow of gas clouds and stellar clusters spreading out toward the galactic center. Light is the ruler. Light has always been the ruler. That assumption sat at the foundation of every map, every textbook diagram, every animated infographic of our spiral home that you've ever seen rotating smoothly in a science documentary. The problem is that between Earth and the galactic center, space is not empty. It is full of dust, not poetic, metaphorical dust, actual dense molecular clouds, vast curtains of interstellar particles, hundreds of light years thick, stacked between us and the core of the Milky Way like layers of frosted glass, and visible light. The very thing we relied on for a century of measurement gets absorbed and scattered by that dust with brutal efficiency. Photons that leave the galactic center carrying precise positional data travel 25,000 light-years, only to be swallowed by molecular clouds long before they reach our instruments. What arrives at our telescopes is dimmed, reddened, distorted, not the real signal, an echo of an echo. Think about what that actually means for the measurement. Imagine trying to gauge the height of the Empire State Building from across the river in New Jersey on a day when dense fog rolls in from the Atlantic. You can see something tall through the haze. You can estimate. But what you're measuring is the silhouette inside the fog, not the building itself. Every number you write down carries the fog's distortion baked into it. Now imagine doing that for 50 years and publishing those numbers in every astronomy textbook on Earth without ever flagging the fog as a serious problem. That is more or less what happened. For decades, the accepted distance from our solar system to the center of the Milky Way hovered somewhere between 26,000 and 28,000 light-years. That range wasn't a secret or a controversy. It was the consensus. It appeared in NASA literature, in university curricula, in popular science books. The International Astronomical Union officially adopted 26,000 light-years as the standard value. Entire models of galactic structure, stellar dynamics, and dark matter distribution were built on top of that number. Then the VLBI Exploration of Radio Astrometry Project, VERA, started measuring differently. VERA is a Japanese radio astronomy initiative that uses very long baseline interferometry, a technique where multiple radio telescopes spread across vast distances work in concert to achieve extraordinary angular resolution. Radio waves, unlike visible light, are not stopped by dust. They travel straight through molecular clouds, through the galactic fog, and arrive at our antennas carrying clean, unscattered positional data. VERA specifically targeted astrophysical masers, natural radio sources produced by molecules like water and methanol in star-forming regions throughout the galaxy. These masers act like precision radio beacons embedded across the Milky Way, and by tracking their positions with interferometry, astronomers can triangulate distances with a level of accuracy that optical methods simply cannot match through thick dust. In 2020, the VERA collaboration published their analysis, combining data from over 99 major sources distributed across the galaxy. The result was a revised, far more precise measurement of our galactic address 25,800 light-years from the Galactic Center. Not 26,000, not 27,000, 25,800. At first glance, that sounds like a minor correction. A few hundred light-years here or there on a galaxy 30,000 light-years across. Surely that's just refining a good estimate, not rewriting the map. But here is where the chain reaction begins. A distance measurement is never just a distance measurement in astronomy. It is a load-bearing number. Every calculation downstream depends on it. The orbital periods of stars near the galactic core, the inferred mass of the central black hole, the density distribution of dark matter throughout the galactic halo, the total mass of the Milky Way itself. When the foundation shifts by 2,000 light-years, everything built on top of it has to be checked, adjusted, or rebuilt. The correction isn't a rounding error. It is the difference between where we thought we were and where we actually are. 2,000 light-years closer to one of the most extreme environments in the known universe. Now ask yourself something, not a comfortable question, a real one. If the most basic number in galactic astronomy, the distance from our own planet to the center of our own galaxy, the one we've had more than a century to measure, was off by 2,000 light-years. And we only found out in 2020 because we finally used the right kind of light to look. What else are we measuring with the wrong instrument? What other foundational numbers in our models of the universe are built on visible light data taken through dust? We didn't fully account for. The Vera result isn't just a correction to one figure. It is a formal announcement that the method we trusted for generations had a systematic flaw we underestimated, and that our cosmic map needs to be redrawn from the inside out. There is something almost comedic about this situation. If you're willing to sit with the irony for a moment, humanity built GPS satellites precise enough to locate your phone within a few feet anywhere on the surface of a planet. We engineered lasers that bounce off the moon and return precise measurements of its distance down to centimeters. We can track the orbit of an asteroid years before it comes anywhere near Earth. And yet, for 50 years, we had the wrong address for our own home in the galaxy, not slightly wrong, 2,000 light-years wrong, and the reason was something as mundane as clouds of space dust blocking the view. We didn't have a sophisticated failure. We had the cosmic equivalent of forgetting to wipe the window before trying to read the street sign. No one sent an update. The textbooks kept printing the old number. What the Vera result represents, stripped of all the technical language, is a reminder that precision in science is only as good as the method behind it. Visible light astronomy gave us extraordinary knowledge about the universe. It also gave us a century of maps drawn through a filter we didn't fully understand. Radio astronomy, infrared observation, and interferometry are now doing what generations of optical telescopes could not. They are seeing through the dust, reading the galaxy directly, and finding that reality does not match the diagram on the wall. The map is being rewritten, the address is changing, and 2,000 light-years closer to the Galactic Center means we are not quite as safely removed from what happens there as we assumed. The shorter distance is not just a number, it means we are moving faster towards something we don't yet fully understand. The orbital speed of our solar system around the center of the Milky Way has been taught as approximately 220 kilometers per second. That number appeared in textbooks, in NASA fact sheets, in every introductory astronomy course taught at every university for decades. It was the established value, not controversial, not provisional settled. The same Vera collaboration that revised our distance to the Galactic Center in 2020 also produced a new measurement of that orbital velocity. The updated figure, 227 kilometers per second, 7 kilometers per second, faster than the accepted standard. Go ahead and think what you're already thinking. 7 kilometers per second on a speed of 220, that's barely 3%. You've tolerated larger errors in your car's speedometer without losing sleep over it. 3% sounds like noise, like the margin of uncertainty you'd expect from measurements made across thousands of light years. Not worth a second thought. Here is why that reaction, completely understandable as it is, misses the point entirely. Your car's speedometer being 3% off means you're going 61.5 miles per hour when you think you're going 60. The error accumulates over a road trip, over a long enough drive. You arrive slightly later than expected, mildly inconvenient, entirely forgettable. The solar system's speedometer being 3% off means something categorically different. We complete one orbit around the Galactic Center approximately every 225 million years. That is one galactic year. In the time it takes us to lap the center of the Milky Way, once, dinosaurs rose, dominated the planet for 160 million years, and went extinct, and that was still only part of a single orbit. Now take a 3% speed discrepancy and run it across that timescale. The accumulated positional difference over one galactic year, is not trivial. It reshapes where we expect to be at any given point in our orbit. It changes our calculated trajectory through the galaxy. And more importantly, it changes the gravitational math. Here is why the speed matters so much. Orbital velocity and gravitational pull are not independent variables. They are locked together by physics. An object orbiting a gravitational center at a specific distance must travel at exactly the speed that balances centripetal force against gravity. Too slow and it spirals inward. Too fast and it drifts outward. The fact that we are actually orbiting at 227 kilometers per second rather than 220 means one of two things must be true. Either the gravitational pull at our distance from the galactic center is stronger than our models predicted, which means there is more mass inside our orbital radius than we accounted for, or the distribution of dark matter in the galactic halo is shaped differently than our current models assume, pulling on us in ways that the standard profile does not capture. Either way, the 3% velocity correction is not a rounding adjustment. It is a signal from the data that the mass model of the Milky Way needs revision. The gravitational architecture of our entire galaxy, how mass is distributed from the dense central bulge out through the spiral arms and into the diffuse dark matter halo, was calculated using the old speed. Plug in the new speed and the equations no longer balance the same way. The three-dimensional mass map of the Milky Way, which every model of galactic evolution and dark matter distribution depends on, must be recalculated. This is what a 3% difference looks like when it sits inside a gravitational equation applied to a structure 400 light-years across and 4 billion years old. The Vera measurements did not just give us a new number for our speed. They exposed a gap between what our models predicted we should be doing and what we are actually doing. Models that were built, again, on visible light data filtered through dust we did not fully account for. The new radio astrometry data is not contradicting the laws of physics. It is revealing that our input parameters were wrong, and that the galaxy we thought we understood has a slightly different mass profile than the one we drew on paper. What does a corrected mass profile mean in practice? It means the galactic rotation curved the graph of how fast stars at different distances from the center orbit the Milky Way has to be refitted. The evidence for dark matter in our galaxy comes primarily from that rotation curve, from the fact that stars far from the center orbit faster than they should if only visible matter were providing gravity. The new speed measurement tightens the constraints on how much dark matter there is and where it must be located. A 3% velocity change at our orbital radius propagates through the entire dark matter model like a thread pulled loose from the edge of a fabric. And there is a second consequence, quieter, but just as significant. If our speed is slightly higher than assumed, then every stellar proper motion measurement, every calculation of how fast a particular star is moving relative to us, was made against a slightly wrong baseline. We measure stellar motion relative to our own motion. get our motion wrong, and every relative measurement inherits that error. The catalog of stellar velocities in the Milky Way, built over more than a century of observation, may contain a systematic offset that runs through it end to end. The map is not just being redrawn. The coordinate system the map was drawn in is being recalibrated. You might be wondering reasonably why this took so long to catch. The answer is not incompetence. It is instrumentation. Radio interferometry at the precision level Vera operates requires an array of telescopes separated by hundreds to thousands of kilometers, coordinated with atomic clock precision, processing signals that correspond to source positions measured in micro-arcseconds. The technology to do this at galactic scales simply did not exist until the last few decades. Previous astronomers were not wrong to use visible light. It was what they had. They were wrong to assume its limitations were fully understood, especially through an interstellar medium whose dust density and distribution we are still actively mapping. What 2020 gave us, between the corrected distance and the corrected speed, is a new starting point, a more honest one. We are 25,800 light years from the center, traveling at 227 kilometers per second. On a map that is being redrawn in real time. And at the center of that map being redrawn, there is something that weighs 4 million times what our sun weighs, sitting quietly, waiting. A black hole cannot be seen directly. That sentence sounds almost philosophical, but it is a hard physical fact. No light escapes from within the event horizon, which means there is nothing for a telescope to detect at the source itself. For most of the 20th century, the existence of supermassive black holes was inferred pieced together from the behavior of surrounding gas, the orbits of nearby stars, the X-ray flares that erupt when matter falls in and releases energy on its way down. Scientists were certain Sagittarius A star existed at the center of our galaxy. They had overwhelming indirect evidence, but no one had ever seen it. That changed in May of 2022. The Event Horizon Telescope Collaboration, a planet-spanning network of radio observatories linked together through a technique called Very Long Baseline Interferometry, effectively creating a telescope the size of Earth, released the first direct image of Sagittarius A star. What the image showed was a glowing ring of superheated plasma, orange and asymmetric, surrounding a dark central region. The ring measured approximately 52 micro-arcseconds in angular diameter as seen from Earth. To put that in perspective, 52 micro-arcseconds is roughly the angular size of a donut sitting on the surface of the moon, as viewed from your backyard. That is the level of resolution the Event Horizon Telescope had to achieve to capture this image. The image confirmed what decades of orbital data had already strongly suggested about the object's mass, 4.154 million times the mass of our sun. Not approximately 4 million, 4.154 million. The imaging data tightened the measurement to a precision that no previous method had reached. Sit with that number for a moment. Our sun contains 99.8% of all the mass in the solar system. It is so massive that its gravity holds 8 planets, hundreds of moons, and countless smaller bodies in stable orbits across billions of miles. And Sagittarius A star contains the equivalent of 4.154 million of those suns, compressed into a region of space defined by its event horizon, the boundary beyond which nothing, including light, returns. That boundary, the event horizon of Sagittarius A star, has a Schwarzschild radius of approximately 12.4 million kilometers. The diameter of our sun is about 1.4 million kilometers. The event horizon of Sagittarius A star is therefore roughly 17 times wider than the sun itself. If you were to remove our sun and place Sagittarius A star at the center of our solar system in its position, the event horizon would extend well past the orbit of Mercury. Mercury's average orbital distance from the sun is approximately 57.9 million kilometers. The event horizon of Sagittarius A star, with a diameter of about 24.8 million kilometers, would not quite reach Mercury's orbit. But the tidal forces, the accretion disk radiation, and the gravitational distortion would render the inner solar system completely uninhabitable. Mercury would be skimming the edge of a gravitational abyss. Venus would be irradiated beyond recognition. Earth would not exist in any form recognizable to us. This is the object sitting at the center of our galaxy. Not a metaphor, not a theoretical construct, a real, confirmed, directly imaged 4 million solar mass singularity, 25,800 light years away, around which everything in the Milky Way, including our solar system, is ultimately orbiting. What makes the 2022 image particularly significant is not just the visual confirmation. It is what the image's properties revealed about the environment immediately surrounding the black hole. The ring structure visible in the image is produced by photons that travel so close to the event horizon that they are bent into near-circular paths before escaping outward. The fact that this ring appears relatively smooth and symmetric told astronomers something important. The plasma environment around Sagittarius A star is turbulent on timescales of minutes to hours, far faster than around M87 star, the other black hole the Event Horizon Telescope previously imaged. SGREA star's accretion environment changes faster than it takes to complete a single telescope observation. The EHT team had to develop entirely new imaging algorithms to handle data where the source itself was visibly varying during the exposure window. It was like trying to photograph a flame in a windstorm using a camera that required a 5-minute shutter speed. And yet they got the image, clear, confirmed, real. Now consider what surrounds this object. That is where the physics stops being merely impressive and starts being genuinely strange. The region within a few light years of Sagittarius A star is not empty. It is not a sterile exclusion zone where gravity and radiation have swept everything clean. It is, improbably, populated. Stars orbit there, young ones, stars with no business existing in that environment, circling a 4 million solar mass black hole at distances that should make stellar formation physically impossible. They are there anyway. Around a monster confirmed by direct imaging, whose event horizon swallows the equivalent of 17 solar diameters, whose accretion environment fluctuates on timescales faster than a working day. Young stars are calmly completing their orbits as if nothing unusual is happening, as if they grew up in a quiet nursery rather than one of the most violent gravitational environments in the known galaxy. One of those stars has an orbit so extreme, a speed so staggering, that when astronomers tracked it through periapsis, its closest approach to the black hole, it didn't just confirm the mass of Sagittarius A star, it tested something Einstein wrote down more than a century ago. And one of those stars moves at a speed that forced physicists to sit down and reconsider the entire theory of how stars are born. Star formation requires patience. That is not a poetic observation. It is the underlying physics. A star is born when a cold, dense molecular cloud, mostly hydrogen, becomes gravitationally unstable and begins to collapse inward on itself. The process takes millions of years. The cloud must be cold enough that thermal pressure doesn't blow it apart before gravity can pull it together. It must be dense enough that the inward pull wins over the outward radiation pressure from any nearby energetic sources. The environment must be, in the language of astrophysics, quiescent, relatively undisturbed, shielded from the hard radiation that would heat and disperse the gas before it has time to condense into a protostellar core. Every textbook on stellar evolution agrees on this. Formation requires a cold, quiet cradle. The environment within a few light years of Sagittarius A star is the precise opposite of a cold, quiet cradle. The accretion disk around Sagittarius A star generates intense X-ray and ultraviolet radiation. Not intense the way a UV lamp is intense, intense the way a nuclear detonation is intense, scaled up and sustained continuously. This radiation field bathes the surrounding region with enough energy to photoionize and thermally evaporate molecular gas clouds long before they can achieve the densities required to begin gravitational collapse. The tidal forces from a 4 million solar mass object at close range are violent enough to shear apart any gas cloud that drifts too near. Turbulence from stellar winds, magnetic field fluctuations, and the dynamical chaos of dozens of massive stars already in tight orbits creates an environment where the fragile, slow process of star formation should be systematically destroyed before it begins. In the 1990s, when astronomers began resolving individual stars in the Galactic Center with adaptive optics on large ground-based telescopes, they expected to find old stars, red giants, ancient remnants of a stellar population that formed long ago, when the central region was calmer and had simply persisted. What they found instead was a cluster of young, hot, massive stars, the S stars orbiting within a fraction of a light year of Sagittarius A star itself. Young in astronomical terms means recently formed. Their spectra showed the unmistakable signature of blue stars in early evolutionary stages, with estimated ages of only a few million years. Among them is S2, also cataloged as S02, the most closely monitored star in the history of stellar astronomy. SA2 orbits Sagittarius A star with a period of 16.05 years, 16 years. Our solar system takes 225 million years to complete one orbit around the galactic center. S2 laps Sagittarius A star more than 14 million times in the same interval. Its orbit is highly elliptical. At its farthest point, it reaches a distance of roughly 10 light days from the black hole. At its closest approach, periapsis, it closes to approximately 120 astronomical units. 1 astronomical unit is the average distance from Earth to the Sun, approximately 93 million miles. Pluto orbits the Sun at an average distance of about 39.5 astronomical units. S2 approaches a 4 million solar mass black hole to within 120 astronomical units, closer than 3 times Pluto's distance from our own Sun, but next to something 4 million times more massive. At periapsis, S2 reaches a peak orbital velocity of approximately 7,650 kilometers per second. That is 2.55% of the speed of light. In more tangible terms, 7,650 kilometers per second means S2 covers a distance equal to the circumference of Earth in roughly 5 seconds. It is the fastest moving star ever directly tracked by human astronomers. And this star is approximately 6 million years old. 6 million years is young. Cosmically, embarrassingly young. The Himalayas are older. The genus Homo was already walking upright on Earth when S2 was forming, if it formed near where it currently orbits, which is the core of the paradox. The radiation environment that should prevent star formation near Sagittarius A star has not changed meaningfully in 6 million years. The tidal forces were there. The X-ray flux was there. The turbulence was there. None of that is new. If the environment was hostile to star formation then, and it was S2, should not have been able to form anywhere near its current orbit. The most credible explanation currently on the table is that S2 did not form where we find it. The hypothesis proposes that the S stars formed much farther out at distances of several light years from the galactic center, in molecular clouds dense and cold enough to support normal star formation. Then, through a process of multi-body gravitational interactions, they were flung inward onto tightly bound orbits close to Sagittarius A star, a passing cluster of massive stars, or a binary star system disrupted by the black hole's gravity. could provide the gravitational kick required. The black hole captures one star in a tight orbit while ejecting the other at high speed, a mechanism called the Hills mechanism. Proposed by astronomer Jack Hills in 1988, it is a plausible mechanism. It has theoretical support, but it has not been directly confirmed. No one has caught this process in action. No one has traced S2's orbit back to a specific birthplace. For now, the paradox of youth remains exactly that, a paradox. The star is here, young, fast, and deeply puzzling. And the explanation for its existence near the Galactic Center is still a hypothesis rather than a solved problem. What is solved? Or rather, what was confirmed beyond reasonable doubt in 2018 is something else entirely. When S2 passed through periapsis in 2018, its closest approach to SGR A star, screaming past at 2.55% of the speed of light at a distance of 120 astronomical units from a 4 million solar mass singularity teams from UCLA and the European Southern Observatory were watching with every precision instrument available. They measured the spectrum of S2's light with extraordinary care, tracking not just the Doppler shift from its orbital motion, but a subtler effect, the gravitational redshift predicted by Einstein's general theory of relativity. Gravitational redshift occurs because photons climbing out of a deep gravitational well lose energy in the process. Energy in a photon corresponds to frequency, and frequency corresponds to color. Photons escaping from near a massive object are stretched toward the red end of the spectrum. Not because the source is moving away, but because gravity itself is sapping the energy from light as it climbs outward. Einstein's theory predicted this effect in 1915. It had been confirmed in Earth's gravity, in the gravity of white dwarfs, but no one had confirmed it directly in the gravitational field of a supermassive black hole until S2 provided the opportunity. The 2018 observations confirmed it. The gravitational redshift in S2's light, measured at periapsis, matched the prediction of general relativity to within the measurement uncertainties. It was the first direct test of Einstein's theory in the extreme gravitational environment of a supermassive black hole, made possible entirely because a 6 million-year-old star happened to orbit in a place where it statistically should not exist. S2 became, without volunteering for the role, the most expensive physics experiment ever conducted, running on orbital mechanics and funded by nothing but gravitational necessity. It had no idea it was checking Einstein's math. It was just doing what its orbit required. The paradox of its youth remains open. The confirmation of relativity stands. And both of those facts point in the same direction. The region around Sagittarius A star contains things that should not be there, behaving in ways that stress test our best theories, and giving up answers to questions we barely knew how to ask. But S2 is a star, and circling the same black hole are things far stranger, things no one has yet been able to name with any certainty. When a physical object approaches a black hole closely enough, tidal forces take over. The side of the object nearest the black hole experiences significantly stronger gravitational pull than the far side. That differential gravity pulling harder on the near end than the far end stretches the object along the radial direction while compressing it laterally. Given enough proximity, the stretching becomes catastrophic. Gas clouds shred. Solid bodies elongate into thin streams of debris. Even stars, held together by their own internal pressure and nuclear energy, get drawn out into long filaments of plasma that spiral inward and eventually feed the black hole's accretion disk. Physicists call this process spaghettification. That is not a colloquial nickname. It is the formal term used in peer-reviewed astrophysics literature, and it accurately describes what general relativity predicts for any extended object that strays too close to a sufficiently massive gravitational singularity. In 2014, an object designated G2 swept past Sagittarius A star at a closest approach distance of roughly 2,000 times the black hole's Schwarzschild radius, approximately 2,000 times the radius of the event horizon itself. In absolute terms, that periapsis brought G2 to within a few hundred astronomical units of a 4 million solar mass black hole. By the tidal force calculations that apply to diffuse gas clouds, G2 should have been shredded. Astronomers had been predicting for years, with mounting anticipation, that the encounter would produce a spectacular fireworks display as G2's disrupted material fed into the accretion disk and triggered a burst of X-ray and infrared emission from SGR A star. They set up their instruments. They waited. They watched. G2 was stretched, noticeably, measurably elongated along its orbit as the tidal forces did their work. The leading edge accelerated ahead of the trailing edge, and for a period, the object was visibly extended across a significant arc of its trajectory. The predicted disruption seemed to be underway. Then EG2 reassembled. It pulled back together, recompacted, and continued along its orbit essentially intact. The fireworks display never came. SGR A star barely reacted. G2 survived an encounter with a 4 million solar mass black hole at 2,000 Schwarzschild radii and came out the other side in one piece. No diffuse gas cloud does that. The physics is unambiguous on this point. A pure gas cloud at that proximity would not have the internal binding energy to resist the tidal forces and reconstitute itself afterward. Something inside G2 was holding it together. Something dense enough and gravitationally bound enough to survive where a cloud alone would not. G2 is not alone. Astronomers have now identified 6 objects of this type, cataloged G1 through G6, all of them orbiting within the innermost region of the Galactic Center. All 6 share the same deeply strange profile they move through space on stellar-type orbits gravitationally governed, elliptical, following trajectories determined by a central massive body. But they appear in infrared observations as extended, diffuse objects. They look like gas clouds that are slowly expanding and dispersing. They occupy a category that should not exist. In the binary taxonomy of Galactic Center objects, a thing is either a star compact, self-gravitating, point-like, or a gas cloud diffuse, extended, easily disrupted. The G objects are apparently both, simultaneously, and neither classification fits cleanly. The leading explanation, developed and published by a team at UCLA in 2020, proposes that the G objects are the products of stellar mergers. In the dense, dynamically chaotic environment of the Galactic Center, close encounters between stars and binary systems are far more common than in the quiet outer galaxy. When 2 stars in a binary system interact with the tidal field of Sagittarius A star, the black hole can perturb the binary's orbit and drive the 2 stars into a collision. The resulting merger produces a single stellar core, dense, compact, held together by its own nuclear fusion. But the collision also generates an enormous envelope of expelled gas and dust that surrounds the merged star for millions of years before it fully dissipates. From a distance, this object looks like an expanding gas cloud. Under the surface, it has the structural integrity of a star. That dual nature explains G2's survival. The stretched, extended appearance during its periapsis passage was the outer gas envelope responding to tidal forces being pulled and distorted as any cloud would be. But the dense, merged stellar core at the center held firm, providing the gravitational anchor that allowed the envelope to recompact after periapsis. The black hole grabbed the wrapper, not the contents. The contents walked away. This hypothesis elegantly accounts for both the cloud-like appearance and the survival. It also makes a prediction the G objects should be infrared bright, not just from reflected radiation, but from internal stellar luminosity. the merged star heating the surrounding envelope from within. Observational data from the Keck Observatory and the Very Large Telescope are consistent with this picture, though definitively resolving the central stellar core from within the gas envelope remains at the edge of current instrumental capability. Now sit with the real question. This raises not the technical one about merger products and tidal survival, but the fundamental one about consequence. What happens to a merged stellar product after it survives periapsis? G2 did not fall in. It was not consumed. It completed its closest approach, endured tidal stretching, recompacted, and continued on its elliptical orbit, which will eventually carry it back outward, away from SGR A star, into the broader Galactic Center environment. It left the encounter with whatever orbital energy its trajectory carried. The merger event that created it in the first place released energy, the kinetic energy of two colliding stars converted into heat, radiation, and the structural reconfiguration of a new single object. That energy went somewhere, into the luminosity of the merged star, into the expanding gas envelope, into the dynamical properties of whatever the merged object eventually becomes as the envelope disperses and the stellar core is exposed. In a system as densely interconnected as the Galactic Center, energy is never lost. It propagates. The merger creates the G object. The G object survives periapsis. The G object disperses its envelope. The stellar core eventually evolves, and every stage of that process feeds something back into the environment, which brings us to an invisible wall that nobody predicted, standing in the middle of the galaxy, blocking things that were supposed to pass through unimpeded. If G2 is a merged star that survived, then the energy from that merger went nowhere. It was released, and that leads directly to a barrier nobody expected. Cosmic rays are among the most energetic particles in the known universe. Protons, atomic nuclei, and electrons accelerated to near-light speeds by supernova shock waves, pulsar winds, and other violent astrophysical processes. They travel in straight lines through interstellar space, cutting through gas clouds, magnetic fields, and vast stretches of vacuum with virtually no deceleration. A sufficiently energetic cosmic ray proton can carry as much kinetic energy as a well-thrown baseball compressed into a single subatomic particle. They do not stop easily. They do not take detours. They propagate through the galaxy as if most of what the galaxy contains is simply not there. Given that description, you would reasonably expect the region around the most energetic environment in the Milky Way, the Galactic Center, with its supermassive black hole, its stellar winds, its accretion activity, its documented history of enormous energy outbursts to be saturated with cosmic rays. If anything in the galaxy is generating high-energy particles and flinging them outward, it is the central few hundred light years. The cosmic ray density at the Galactic Center should be at least as high as the galactic average, and almost certainly higher. The observations say otherwise. Data from the High Energy Stereoscopic System, HESS, a ground-based gamma-ray telescope array located in Namibia, and from NASA's Fermi Gamma Ray Space Telescope, converge on a result that should not exist: the central molecular zone, the dense ring of molecular gas clouds surrounding the Galactic Center with a radius of roughly 600 light-years, shows a cosmic ray density profile that is sharply and systematically different from the surrounding galactic disk. Not slightly different, not within measurement uncertainty. The boundary is clean enough, and the discrepancy large enough to demand a physical explanation. The measurement method is indirect but reliable. When high-energy cosmic ray protons collide with the nuclei in dense molecular gas clouds, they produce gamma rays through a process called pion decay. The intensity of this gamma ray emission depends on two things: the density of the gas, which can be measured independently through radio and infrared observations, and the local density of cosmic rays. If you know the gas density and you measure the gamma ray intensity, you can back calculate the cosmic ray density in that region. HESS and Fermi have done exactly this across the central molecular zone, comparing the derived cosmic ray densities inside the CMZ with those measured in adjacent regions of the galactic disk. The cosmic ray density inside the CMZ is significantly lower than what models without any barrier would predict. The particles are not getting in at the rate they should be, given the sources available and the propagation physics that works everywhere else in the galaxy. Something at the boundary of the central molecular zone is reducing the flux of incoming cosmic rays selectively, consistently, across a region spanning hundreds of light years. Think about what that boundary feels like conceptually. Step outside on a day when the temperature is 100 degrees Fahrenheit and walk into a perfectly air-conditioned building. The moment you cross the threshold, the environment changes completely. You know a boundary exists because you can feel the difference on either side. But you cannot see the air conditioning itself, no visible line, no physical barrier you could reach out and touch. You just know something is maintaining that difference, actively, continuously, against the natural tendency of heat to equalize across the barrier. The central molecular zone is the cold room. The rest of the galaxy is the summer heat outside, and something is keeping the door closed. The confirmation of this barrier through gamma-ray emission analysis is not a single telescope result or a tentative preliminary finding. Multiple independent observational campaigns, using different instruments and different analysis approaches, agree that the cosmic ray deficit inside the CMZ is real. The HESS collaboration's detailed spatial mapping of the central galactic region, published over the course of the 2010s, showed not just that the CMZ has lower cosmic ray density, but that the density gradient at the boundary is steep. The transition from outside to inside happens over a relatively narrow spatial range, consistent with an active barrier mechanism rather than simple diffusion effects. What makes this finding particularly striking is the location. The CMZ is not some quiet backwater. It contains some of the most massive molecular clouds in the galaxy, enormous star-forming complexes, the central molecular zone's own populations of young massive stars, and it sits directly around Sagittarius A star. This is the most energetically active region of the Milky Way. The energy output from stellar winds, supernova remnants, and the black hole itself within this region is enormous. And yet cosmic rays from outside from the broader galactic disk are being kept out. The Galactic Center is not just generating energy outward. Something is also preventing energy from getting in. That asymmetry is the heart of the mystery, and the two candidate explanations for what is maintaining that asymmetry are so different in their physical mechanisms and so consequential in their implications that they have split the astrophysics community into two camps that are not yet close to agreeing. But what is actually building that wall? The answer splits science into two sides with no common ground. The central molecular zone's magnetic field is not merely strong. It is strong in a way that requires a moment to properly absorb. Measurements using radiopolarimetry and infrared polarization of dust emission consistently show magnetic field strengths in the CMZ reaching into the milligauss range, that is, on the order of 1 milligauss throughout much of the region, with localized areas potentially higher. The average magnetic field strength in the galactic disk, out in the quiet spiral arms where our solar system resides, is roughly a few microgauss. 1 milligauss is 1,000 microgauss. The CMZ's magnetic field is therefore somewhere between several hundred and several thousand times stronger than the field threading the ordinary galactic disk. That difference matters enormously for cosmic ray behavior. A charged particle moving through a magnetic field does not travel in a straight line. The Lorentz force deflects it, bending its trajectory perpendicular to both its velocity and the field direction. For a weak field, like the one in the outer galactic disk. This deflection is mild cosmic rays curve gently, drift slowly, and diffuse through the galaxy over millions of years, but ultimately penetrate everywhere. The field is not strong enough to stop them. It redirects them, but it does not wall them out. A Milagos field is a different regime entirely. Charged particles entering a Milagos field face deflection forces orders of magnitude larger than what they experience in the outer disk. Their gyro radius, the radius of the circular or helical path they follow, while spiraling around magnetic field lines, shrinks dramatically. Instead of drifting freely through the field, particles become tightly wound around field lines, constrained to follow the magnetic geometry rather than propagating freely. If the field lines in the CMZ are organized, structured coherently on large scales, rather than tangled and chaotic, they can act as a mesh, channeling particles along specific paths, or reflecting them back outward before they penetrate deeply into the zone. Think of Earth's magnetosphere. Our planet's magnetic field, generated by the churning iron in the outer core, extends tens of thousands of kilometers into space and deflects the solar wind, the continuous stream of charged particles flowing outward from the sun. The solar wind is not stopped by Earth's magnetic field in the sense of being physically blocked by a wall. Instead, it is deflected around the magnetosphere, channeled into the polar regions where field lines converge, and partially reflected back. The Van Allen radiation belts are the trapped remnant of particles that got caught in the magnetic geometry and could not escape. The magnetosphere shields Earth's surface from the full brunt of solar particle bombardment. The CMZ's magnetic barrier works on the same physical principle. The scale is just incomparably larger, hundreds of light years, rather than tens of thousands of kilometers. And the particles being deflected are cosmic rays with energies vastly higher than anything the solar wind carries. But the mechanism, a structured, strong magnetic field redirecting charged particles, is the same physics that protects life on Earth from solar particle radiation, operating at galactic scale. That is Hypothesis 1, coherent, well supported by field strength measurements, grounded in established physics. Hypothesis 2 starts from a different place entirely. Sagittarius A star, even in its current relatively quiescent state, is not truly passive. Material falling toward the black hole, stellar winds from the dense population of massive young stars in the central parsec, and the general energetic activity of the Galactic Center collectively drive an outflow, a galactic wind that streams continuously outward from the central region into the surrounding galaxy. The energy injected into this outflow comes from multiple sources: radiation pressure on dust and gas, the thermodynamic pressure of hot plasma heated by stellar winds and supernova remnants, and possibly contributions from past periods of higher accretion activity by SGR A star itself. This outward flowing galactic wind acts on incoming cosmic rays the way the solar wind acts on interstellar dust particles approaching the solar system. The solar wind carries a magnetic field with it as it blows outward from the sun, and this magnetized wind sweeps through the heliosphere, pushing back against particles trying to diffuse inward. Interstellar cosmic rays must fight against this outward flow to penetrate into the inner solar system, and lower energy particles lose that fight, excluded from the inner heliosphere by what is called the solar modulation effect. Higher energy particles, with more momentum to push against the wind, make it through. Lower energy ones do not. The galactic wind from the CMZ creates an analogous situation at a vastly larger scale. Cosmic rays from the outer galactic disk, trying to diffuse inward toward the galactic center, are meeting an outward flowing wind of magnetized plasma. The wind's ram pressure and its carried magnetic field combine to impede inward diffusion, effectively reducing the penetration of lower energy cosmic rays into the CMZ below what simple diffusion models would predict. The barrier is not a static magnetic wall. It is a dynamic pressure balance between inflow and outflow, maintained actively by the energy output of the galactic center itself. Now for the part that should make you genuinely uncomfortable. These two mechanisms, the Milky magnetic field deflecting cosmic rays and the galactic wind pushing them back, are not mutually exclusive. There is no physical reason why both cannot be operating simultaneously. In fact, they are likely coupled. The galactic wind carries the magnetic field with it as it flows outward, meaning the structured magnetic geometry and the outward wind pressure reinforce each other. The real barrier may be a composite system, a combination of static magnetic deflection and dynamic wind pressure, woven together into something more complex than either hypothesis alone describes. And if that is the case, we currently have no simulation capable of fully modeling it. The computational demands of running magnetohydrodynamic simulations for a region spanning hundreds of light years, with the spatial resolution required to capture the relevant physics, at the timescales over which the barrier operates, exceed what current supercomputers can handle in any practical sense. We know the wall is there. We have two solid candidates for what holds it up. We cannot yet build the model that would tell us which one dominates, how stable the barrier is, or under what conditions it might weaken. That last question deserves attention. If the barrier weakened, if the magnetic field became less organized, or the galactic wind temporarily diminished cosmic rays from the inner galaxy, where Sagittarius A star and the dense stellar population generate them in abundance, would diffuse outward more effectively into the galactic disk. Conversely, cosmic rays from the disk would penetrate more deeply into the CMZ. Either direction means the current equilibrium dissolves. The regions on both sides of the barrier would be exposed to particle fluxes they are not currently experiencing. Our solar system sits in the disk, 25,800 light-years out, well outside the CMZ, but well outside has a different meaning when the thing you are outside of has a barrier whose stability is not guaranteed. As it turns out, the Galactic Center has spent decades being admired for its apparent restraint, a sleeping giant that could awaken but hasn't lately. And scientists, half relieved, noted at least one silver lining. The center seems to be keeping its worst energies contained, protecting the rest of the galaxy from itself. In a universe full of active galactic nuclei blasting jets across millions of light years, we got a quiet one. The Galactic Center is basically running its own containment protocol, and the rest of the galaxy is counting on it to hold. But even when the wall holds perfectly, the radiation from the galactic core does not stay contained. It leaks outward in a form no optical telescope on Earth can detect with unaided instruments. And it has been accumulating in the data for years, waiting for someone to realize what they were looking at. But even when the wall holds radiation from the core, is still leaking outward in a form no telescope on Earth can see with naked optics. Gamma rays sit at the extreme end of the electromagnetic spectrum. They carry the highest energies, the shortest wavelengths, and they are produced only by the most violent processes. The universe runs nuclear decay inside atoms, matter-antimatter annihilation, particles accelerated to near-light speed in supernova shockwaves, the relativistic jets of active black holes. Gamma rays do not come from gentle processes. Every gamma-ray photon is a record of something extreme happening somewhere. They pass through ordinary matter, through dust clouds, through gas, through the interstellar medium far more easily than visible light or even X-rays, which means when a gamma-ray telescope detects a signal, it is reading the source almost directly, with minimal distortion from the intervening material. This is why what NASA's Fermi Gamma-Ray Space Telescope found at the center of the Milky Way has been generating sustained scientific controversy since it was first clearly identified in analyses published around 2009 and 2010, and why that controversy has only deepened in the years since. Fermi detected a gamma-ray excess, an extended region centered on the galactic center, glowing in gamma rays at energies of a few to tens of giga-electron volts. That is brighter than what all known astrophysical sources in the region can account for. The excess is not a point source. It is not a single bright object someone missed. It is diffuse, spread over a region several degrees across as seen from Earth, corresponding to a physical extent of thousands of light years around the galactic center. It is bright enough to stand out clearly above the background, even after careful modeling and subtraction of all the gamma ray emission from known sources, cosmic ray interactions with gas, diffuse galactic emission, point sources of various kinds. The excess is smooth. That word carries enormous weight in this context. Astrophysical sources of gamma rays, supernova remnants, pulsar, wind nebulae, molecular clouds being bombarded by cosmic rays. Individual massive stars produce emission that is clumpy, localized, asymmetric. Real sources have structure. They cluster along the galactic plane. They correlate with known molecular cloud distributions. They bunch around regions of recent star formation. You would not expect them to sum to a smooth, extended glow that falls off gradually and uniformly in every direction from the galactic center. The Fermi excess does exactly that. It is spherically symmetric around the galactic center. Its radial profile, how the brightness decreases with increasing distance from the center, follows a smooth power law curve, uniform regardless of which direction you look, north of the galactic plane, south of it, toward the inner galaxy. Toward the outer galaxy, the brightness profile is the same. The emission is centered on the black hole and drops away from it with near-perfect symmetry. Imagine stepping into a completely dark room and turning on a single lamp. If the lamp is working correctly, the brightness it casts falls away uniformly in every direction. The ceiling gets the same illumination as the floor at equal distances. The north wall mirrors the south wall. The room is lit by one symmetric source. Now imagine you enter the room and observe exactly that uniform illumination, falling away with perfect symmetry in all directions. But when you search for the lamp, you find nothing. Every light fixture you check is off. No candles, no phone screens, no glowing electronics. The light is there. The source is invisible. That is, structurally, the situation Fermi presented astronomers with. The gamma ray glow is real, measured, consistent across multiple analyses by independent research groups using different methods and different portions of the Fermi dataset. The symmetry and smoothness are not artifacts of analysis choices. They are robust features of the signal, and no inventory of known gamma ray sources in the galactic center region, however carefully assembled, fully accounts for what Fermi sees. Why does the smoothness matter so much? Because the two candidate explanations for the excess make very different predictions about what the emission should look like spatially. One of those explanations predicts exactly the kind of smooth, symmetric halo centered on the galactic center that Fermi observes. The other predicts that, on fine enough angular scales, the apparent smoothness should break down into a collection of individually unresolved point sources too faint and too numerous for current instruments to separate, but statistically distinguishable from a truly diffuse emission if the data are analyzed with sufficient care. The question of which description fits the data better has been fought over, extensively and loudly, in the astrophysics literature since at least 2014. The answer determines whether the Fermi gamma ray excess is the first confirmed detection of dark matter particles in the history of physics, or whether it is a large population of rapidly spinning dead stars that we simply cannot resolve individually with current instruments. Both possibilities are extraordinary, one more than the other, and they cannot both be correct. Two explanations, one born from particle physics, one from the graveyard of dead stars, and only one of them can be right. If dark matter is made of weakly interacting massive particles, WIMPs, then two of those particles colliding with each other do not simply scatter, they annihilate. The collision converts both particles entirely into energy, and that energy emerges as other particles, including gamma rays at a characteristic energy determined by the mass of the WIMP itself. The predicted mass range for WIMPs that fits the cosmological evidence for dark matter, the galaxy rotation curves, the large-scale structure of the universe. The cosmic microwave background puts the annihilation gamma ray signal in the range of roughly 30 to 40 giga-electron volts. The Fermi gamma ray excess peaks at energies in the range of roughly 1 to 3 giga-electron volts, with the spectral shape broadly consistent with what WIMP annihilation into bottom quarks, which then decay and produce gamma rays, would generate for a WIMP mass in the tens of giga-electron volts range. The spatial profile, as established in Part 8, is smooth, spherically symmetric, and centered on the galactic center exactly where dark matter density is predicted to peak according to standard halo models like the Navarro-Frank-White profile. The spectrum matches, the morphology matches, the location matches. If this is dark matter annihilation, the implications cannot be overstated. Dark matter constitutes approximately 27% of the total energy content of the universe. It is the gravitational scaffolding around which all visible matter, every galaxy, every star, every planet, every atom you are made of, assembled itself after the Big Bang. We have known it exists through its gravitational effects for decades. We have never directly detected a single dark matter particle, not once, in any laboratory, in any particle detector, in any astrophysical observation that could be unambiguously attributed to dark matter interacting with itself or with ordinary matter. The Fermi excess, if it is WIMP annihilation, would be the very first direct evidence of a dark matter particle in the entire history of physics. That is not a minor result. That is the most significant detection in the history of science, which is precisely why the second explanation deserves to be taken with equal seriousness, no matter how much less romantically it reads. Millisecond pulsars are the ultra-fast spinning remnants of neutron stars that have been spun up by accreting material from a binary companion. They rotate hundreds of times per second, some reaching over 700 rotations per second, and they generate powerful magnetic fields that accelerate particles along their magnetic poles, producing beams of gamma ray emission that sweep through space like lighthouse beams at extraordinary rotational speeds. Individually, each millisecond pulsar is a detectable point source for Fermi. The galaxy contains thousands of them that have already been cataloged. But the Galactic Center is a different environment. The stellar density there is orders of magnitude higher than in the outer disk. Binary star systems are more common. Stellar interactions that produce the neutron star binary companion pairings required to spin a pulsar up to millisecond periods are far more frequent. The theoretical expectation is that the Galactic Center harbors an enormous, unresolved population of millisecond pulsars, potentially on the order of 100,000, hidden in the dust and gas that prevents optical and even many infrared observations from resolving individual faint objects, each one too dim for Fermi to detect individually. All of them together, their collective gamma ray emission summed across 100,000 sources, producing a diffuse glow that looks, on the angular scales Fermi can resolve, smooth and symmetric because the underlying population is distributed smoothly and symmetrically around the galactic center by the same gravitational potential that shapes everything else there. 100,000 invisible lighthouses, each too faint to see individually, all spinning in the same general region, adding their gamma rays together into a single, featureless haze. The sum of 100,000 unresolved point sources looks, at Fermi's resolution, exactly like a diffuse emission region. The critical question is whether the gamma ray excess is truly diffuse, genuinely smooth at all angular scales. as dark matter annihilation would produce, or whether it is merely unresolved. Smooth only because current instruments cannot separate the individual contributions. The statistical technique developed to distinguish these two cases looks at the pixel-to-pixel fluctuations in the Fermi photon count maps. A truly smooth, diffuse source produces Poisson fluctuations, the kind of random variation you get when counting photons from a continuous process. A collection of unresolved point sources produces non-Poissonian fluctuations, a slightly clumpier statistical distribution, because the photons are coming from discrete locations, even if those locations cannot be individually resolved. Statistical analyses published between 2019 and 2022 from multiple independent research groups using different methodological approaches and different portions of the accumulated Fermi dataset found that the photon statistics of the Galactic Center excess are more consistent with non-Poissonian fluctuations, more consistent, in other words, with unresolved point sources than with a truly diffuse, smooth signal. The results from groups at MIT, Princeton, and several European institutions pointed in the same direction. The data statistically prefer the millisecond pulsar interpretation over the dark matter annihilation interpretation, but not decisively, not by the kind of margin that closes a scientific debate. The systematic uncertainties in the analysis are substantial. Modeling the diffuse gamma-ray background in the galactic center region requires assumptions about cosmic ray propagation, gas distribution, and the contribution of other emission components that are themselves uncertain. Different choices of background model produce different residual excesses and different statistical conclusions about the underlying source population. Some analyses find stronger preference for point sources. Others find the dark matter hypothesis cannot be ruled out at any meaningful level. The debate in the literature is genuine, ongoing, and unresolved. You want it to be dark matter. Admit it. Everyone who has spent any time thinking about what 27% of the universe is actually made of wants it to be dark matter. The idea that we stumbled onto the first direct detection, not by building a giant underground detector, but by staring at the center of our own galaxy with a space telescope, is the kind of story physics rarely gets to tell. It has the shape of a great discovery, but science has no interest in what the story should be. It is interested only in what the data say, and the data right now say probably not dark matter, but we cannot be certain, and we do not yet have the instruments to settle it. The resolution may come from the Vera Rubin Observatory, which began science operations in 2024. Rubin's unprecedented survey depth and cadence will help refine the census of millisecond pulsars in the galactic field population, improving the statistical models used to predict how many should exist in the Galactic Center. The next generation of gamma-ray instruments, including proposed successors to Fermi with significantly better angular resolution and sensitivity, are specifically motivated in part by the need to resolve this question. The Cherenkov telescope array, currently under construction, will achieve sensitivity roughly 10 times greater than Fermi in certain energy ranges, potentially capable of resolving individual millisecond pulsar contributions if the population hypothesis is correct. The answer may arrive within this decade, or it may require instruments that do not yet exist. Either outcome is extraordinary. 100,000 spinning stellar corpses lighting up the galactic center in unison that is its own kind of astonishing. But it is not dark matter. And if it is dark matter, then the universe has been quietly annihilating itself in the core of our galaxy for billions of years, leaking the evidence outward as gamma rays, waiting for a species intelligent enough to build a space telescope and look in the right direction. Both possibilities deserve the weight of that sentence. While that debate remains unsettled in 2021, a completely different signal appeared from the direction of the Galactic Center, one that nobody had planned to find. Every radio source in the known universe has a pattern. That is not an assumption or a convenient simplification. It is an empirically established fact, built from decades of systematic radio sky surveys, covering billions of sources. Pulsars flash with metronomic regularity, their rotation periods stable enough to rival atomic clocks, some varying by less than 1 part in 10 to the 13th over years of observation. Magnetars, the most magnetically extreme neutron stars, burst erratically, but within physically understandable frameworks. Their outbursts, governed by the sudden reconfiguration of magnetic field structures that have been building stress over months or years. Fast radio bursts arrive as single millisecond duration pulses or in repeating patterns with identifiable repetition statistics. Variable stars, active galactic nuclei, X-ray binaries, all of them fluctuate, but all of them fluctuate in ways that can be modeled, categorized, and ultimately understood as expressions of known physical processes cycling through recognizable states. In 2021, a doctoral student named Zai-Teng Wang at the University of Sydney was conducting a survey with the Australian Square Kilometre Array Pathfinder telescope when he found something that matched none of those frameworks. The source switched on and off, not regularly, not on any period that repeated. It would emit radio waves for a duration ranging from a few seconds to several minutes, then go silent for an interval that bore no predictable relationship to either the duration of the burst or the previous silence. There was no clock, no cycle, no statistical fingerprint of an underlying periodic process hiding beneath the noise. It simply appeared, lasted for some unpredictable amount of time, and then vanished, with no discernible rule governing when it would return. Wang and his PhD supervisor, astronomer Tara Murphy, named the object informally after the head of the research group. Astronomer Andrew Andy Zick, giving rise to the informal designation Andy's object. Its formal catalog designation is Gleam XJ16275-5.5-52350.4.3, placing it in the direction of the Galactic Center at a distance estimated to be within the inner galaxy. It has since been recognized as part of a broader emerging class of unusual radio transients, identified through programs like the Meerkat Radio Telescope's Galactic Plane Survey and LOFAR's low-frequency monitoring, sometimes grouped under the designations GPM sources or long-period radio transients, though no single classification has yet been formally adopted because the class itself is still being defined. Think about what no discernible period means for an object in this context. Imagine a streetlight in your city that operates on no schedule. Not broken, it produces good. Strong light when it is on, but it turns on for 30 seconds at 3 in the morning, goes dark for 2 hours, turns on again for 7 minutes in the mid-afternoon, stays off for a full week, then suddenly illuminates for 90 seconds at noon on a Tuesday. Power company sends technicians. Nothing wrong with the wiring, nothing wrong with the bulb. The light is working exactly as it was built to work. It just refuses to follow any of the patterns that every other streetlight in the world follows. You watch it for 6 months and never extract a period. No Fourier analysis of the on-off record yields a frequency. The light is doing something, but not something that fits the vocabulary of known electrical behavior. That is the epistemological situation astronomers faced with Andy's object. The emission was real, bright, and coherent, not noise, not an artifact. But the time series of its appearances contained no recoverable period despite extensive analysis. This matters enormously for classification because periodicity is the primary diagnostic tool for identifying compact object radio emitters. Pulsar check for a period in the milliseconds to seconds range. Magnetar check for a period in the seconds to minutes range. Rotating radio transient check for a period in the seconds to hours range. Andy's object refuses to yield a period on any of those scales, or any other. If no period, then not a pulsar by any standard definition. Pulsars are, by definition, periodic. Their emission is the rotational beacon of a spinning neutron star, and that beacon has a period because rotation has a period. A source without a period cannot be a pulsar in the conventional sense. If not a pulsar, then what is it? That question does not yet have a clean answer, and the astrophysics community is honest enough to say so. The candidates that have been proposed include an ultra-long period magnetar, a class of object that theory has predicted might exist, but which had never been clearly observed before this object, and a small number of similar transients began appearing in survey data. An ultra-long period magnetar would be a neutron star with an extremely strong magnetic field that has been spun down so dramatically by magnetic braking that its rotation period has stretched to hundreds or even thousands of seconds, far beyond the range of ordinary pulsars, and potentially so long that the geometry of the emission beam only intersects our line of sight sporadically rather than on each rotation, producing the appearance of irregular bursting rather than steady pulsing. But even that hypothesis is tentative. It fits some of the observed properties and struggles with others. What is not in any doubt is the significance of the aperiodic behavior. In a universe where every radio-emitting compact object we had ever found ticked on some identifiable clock, Andy's object shows up and announces that at least one class of source, and possibly several, does not tick. That is not a small extension to the known catalog. It is a new category of behavior, a new room in the taxonomy of radio-emitting phenomena that nobody had drawn on the map. And it is located, with all its inexplicable irregularity, in the direction of the most densely populated, most magnetically extreme, most dynamically violent region of our entire galaxy. And that is not even the strangest part. Its polarization is what made astronomers genuinely sit up straight. The radio waves from Andy's object are polarized at nearly 100%. That single measurement, not the aperiodic flashing, not the unusual duration, not the location near the Galactic Center, is the detail that made radio astronomers stop what they were doing and look at the data again. To understand why, it helps to understand what polarization actually means for a radio wave. Electromagnetic radiation oscillates. The electric field component of the wave vibrates perpendicular to the direction of travel. In most natural radio sources, the emission comes from countless individual charged particles radiating in different orientations, so the oscillations point in all directions simultaneously, producing what physicists call unpolarized or randomly polarized light. Averaging across all those random orientations, no single direction dominates. The wave carries energy, but no preferred plane of oscillation. Polarized emission is different. When radio waves are highly polarized, linearly polarized, meaning the electric field oscillates preferentially along a single plane, it means the emitting process itself has a preferred geometry, or that the waves have traveled through a medium that imposed order on the oscillations. The most common astrophysical mechanism for producing high linear polarization in radio waves is synchrotron radiation-charged particles, usually electrons, spiraling at relativistic speeds along magnetic field lines. The magnetic field defines the geometry. The spiraling motion produces the radiation, and the radiation inherits the directional structure of the field that shaped the particle's path. The critical word is structure. Synchrotron emission only produces near-complete polarization when the magnetic field itself is coherently organized, aligned in the same direction over the spatial extent of the emitting region. A tangled, turbulent, chaotic magnetic field produces synchrotron emission too, but from different regions, the polarization vectors point in different directions and partially cancel out. reducing the net measured polarization to well below 100%. The higher the degree of linear polarization, the more organized the underlying magnetic field must be. Andes object's polarization fraction sits between approximately 80 and 100% across its observed bursts. That is not the polarization fraction of a moderately organized field. That is the polarization fraction of a magnetic environment that is extraordinarily coherent, structured on scales comparable to or larger than the emitting region, with field lines aligned to a degree that essentially no cancellation occurs. The medium through which these radio waves travel, or the region in which they are produced, contains a magnetic field that is organized more precisely than almost anything else observed in the galaxy. Recall from Part 7 what was said about the magnetic field of the central molecular zone milligas strength fields, several hundred to several thousand times stronger than the galactic disk average, and evidence from radiopolarimetry that portions of that field are coherently structured over large scales. Andes object, located in the direction of the Galactic Center, is emitting radio waves that bear the imprint of exactly that kind of environment. The near-complete polarization is not incidental. It is a fingerprint pressed into the electromagnetic signal by whatever combination of source structure and intervening medium shaped these waves before they reached our antennas. Now cross-reference this polarization data against the known catalog of compact radio sources. The mismatch with every established category is total. Ordinary pulsars produce highly polarized emission that is consistent, but pulsars have rotation periods ranging from roughly 1.4 milliseconds at the fast end to a few seconds at the slow end. Some rotating radio transients have been found with periods stretching to a few minutes. Andes object shows no repeating period at all on any of those timescales, and the individual burst durations of seconds to several minutes are inconsistent with the lighthouse beam geometry of a rotating neutron star unless the rotation period is extraordinarily long. Longer than anything in the pulsar catalog, magnetars produce some of the most intensely polarized radio emission known, and their extreme magnetic fields reaching 10 to the power of 15 Gauss. Compared to a typical neutron star's 10 to the power of 12, are fully capable of generating the kind of coherent field structure that near-complete polarization implies. But magnetar radio bursts have characteristic energy signatures and spectral properties tied to the physical processes of magnetic field reconfiguration starquakes. Field line reconnection events and those properties do not align cleanly with what Andes object produces during its bursts. The energy budget and spectral character of the emission fit imperfectly. Fast radio bursts are another candidate that immediately comes to mind when discussing a transient radio source with high polarization. Some FRBs show very high polarization fractions, and their polarization properties have been used to probe the magnetic environments of their host galaxies. But FRBs are millisecond duration events, single pulses or short burst sequences lasting no more than a few milliseconds. Andes object's bursts last from several seconds to several minutes. That is 3 to 5 orders of magnitude longer than a fast radio burst. The physics that produces an FRB in milliseconds cannot be straightforwardly scaled up to produce a qualitatively similar event that lasts for minutes. The emission mechanism would have to be fundamentally different. The most actively discussed hypothesis, the ultra-long period. Magnetar attempts to bridge these gaps. A neutron star born with an extremely strong magnetic field loses rotational energy rapidly through magnetic dipole radiation, spinning down as the field extracts angular momentum from the rotation. Under extreme conditions, this spin-down process could push the rotation period to hundreds, or theoretically, thousands of seconds far beyond the known pulsar graveyard in period-period derivative diagrams, into a regime where most theoretical models said radio emission should no longer be possible. Yet Andy's object appears to be emitting radio waves from exactly that regime. If the ultra-long period magnetar interpretation is correct, but appears to be is doing significant work in that sentence, the hypothesis is plausible. It is not confirmed. It explains some of the observations while leaving others, including the complete absence of any detectable period without full accounting. The honest position, which the astrophysics community has largely adopted in published literature, is this Andy's object represents either a previously unidentified subtype of known compact object or an entirely new class of astrophysical emitter that requires a description not yet written. Both options are significant. The first would extend our taxonomy of neutron star physics into unexplored parameter space. The second would add a new room to the house of astrophysics, a room that the blueprints said should not be there. The parallel to the discovery of the platypus is genuinely apt, not as a joke, but as an epistemological description. When the first preserved platypus specimen reached European naturalists in 1799, the zoologist George Shaw suspected it was a taxidermist's hoax, a duck's bill sewn onto a beaver's body. The animal violated every organizing principle of mammalian biology that existed at the time. It was not a hoax, it was real, and its existence eventually forced a fundamental revision of how vertebrate biology classified the relationship between reproduction, hair, and warm blood. The taxonomy had to expand to include it. Astronomers looking at Andy's object are, in a very precise sense, in George Shaw's position. The object is real, the data are clean, the measurements are reproducible, and the catalog has no shelf for it yet. What is almost grimly funny about this situation is that the astrophysics community, a field that regularly deals with objects of incomprehensible scale and violence, has been stumped by something that occasionally flashes on and off for a few minutes at a time. The universe found a way to be mysterious, not with a roar, but with an irregular blink. The taxonomist found something furry that lays eggs, and now everyone is arguing about which drawer to put it in. Andy's object is strange, but what comes next is not merely strange. It proves that the Galactic Center once exploded with catastrophic violence, and nobody can guarantee it has stopped. Sagittarius A star, right now, looks quiet. By the standards of supermassive black holes across the universe, it is almost unremarkable in its current state. Active galactic nuclei, the luminous cores of galaxies where supermassive black holes are actively consuming large quantities of material, are visible across billions of light years because of the energy they pour out. Quasars, the most extreme examples, outshine their entire host galaxies by factors of hundreds or thousands, driven by accretion rates that feed matter into the central black hole at rates capable of converting rest mass into radiated energy with extraordinary efficiency. Some AGN launch relativistic jets, collimated streams of plasma, accelerated to near-light speed that extend for millions of light years, reshaping the gas halos around their host galaxies and leaving permanent structural marks on the intergalactic medium. SGR A star does none of that visibly right now. It accretes at a very low rate. It produces occasional X-ray flares, brief brightenings when a clump of gas falls in, but nothing sustained, nothing catastrophic. Compared to the monsters powering distant quasars, it is a sleeping animal. Astronomers who study active galactic nuclei sometimes use SGR A star as a reference point for what a truly quiescent supermassive black hole looks like. In 2010, the Fermi Gamma Ray Space Telescope destroyed that narrative with two enormous structures that had been hiding in plain sight. Extending above and below the plane of the Milky Way, centered precisely on the Galactic Center, Fermi revealed two vast lobes of gamma ray emission, now called the Fermi Bubbles. Each lobe reaches approximately 25,000 light years from the galactic plane. Together, from the tip of the northern bubble to the tip of the southern bubble, The total structure spans roughly 50,000 light years, comparable to the full diameter of the galactic disk itself. The Milky Way's disk of stars and gas is roughly 100,000 light years across and a few thousand light years thick. The Fermi Bubbles are inflated perpendicular to that disk, punching out above and below the galaxy's flat plane like two enormous spheres emerging from the center. Picture the geometry this way. You walk into a room and notice two enormous scorch marks, one on the ceiling directly above the center of the room, one on the floor directly below it. Both marks are roughly the same size, symmetric, centered on the same point. The furniture in the room is undisturbed. The walls are fine, but the ceiling and the floor carry the unmistakable evidence of something that released an enormous amount of energy at the center. And that energy went up and down with equal force. You ask the person sitting calmly at the table in the middle of the room what happened. They say, "I have no idea. I've been sitting here quietly for years." That is the observational situation. The Galactic Center, presently quiet, is bracketed by two structures whose scale and energy content are anything but. The Fermi Bubbles are not cold remnants. They are not ghost structures left behind by some ancient process that has long since cooled and faded. X-ray observations from the Rosat satellite and subsequent instruments revealed that the edges of the bubbles are sharp, not gradual. Diffuse boundaries as you would expect from material that had been expanding and cooling for billions of years, but crisp edges suggesting relatively recent energetic injection that has not yet had time to diffuse and smooth out. The interior of the bubbles contains hot plasma, not warm hot in the astrophysical sense that carries genuine meaning temperatures estimated at tens of millions of degrees, characteristic of material that has been processed through a strong shock wave and thermalized at extremely high energy, the gamma ray emission itself. At the energies Fermi detects it, requires either inverse Compton scattering, where electrons moving at nearly the speed of light transfer energy to lower energy photons, boosting them up to gamma ray energies, or pion decay from cosmic ray protons colliding with gas. Either mechanism requires the presence of highly energetic particles, not the settled debris of an ancient event. Something created these bubbles. Something fed enough energy into the Galactic Center region to drive two symmetrical outflows that punched through the galactic halo and inflated structures 50,000 light-years tall. The numbers involved are staggering. Estimates of the total energy contained in the Fermi Bubbles' kinetic energy of the outflowing gas plus the energy carried by the relativistic particles run to approximately 10 to the power of 55 ergs. For comparison, a typical supernova releases roughly 10 to the power of 51 ergs of energy. The Fermi Bubbles contain the equivalent of approximately 10,000 supernovae worth of energy, deployed in a structured, coherent, directional outflow from the Galactic Center. What was strong enough to do that the answer is not obvious, and it is not agreed upon. It is, in fact, one of the most actively contested questions in galactic astrophysics. Two origin scenarios have the most support, and they point to very different physical processes, one involving a past active phase of SGR A star itself, the other involving the collective output of an entire stellar population. The energy scales are clear. The structures are real, measured, sitting there above and below the galaxy right now as undeniable physical objects. Whatever produced them was operating at a level that dwarfs anything SGR A star is doing today by many orders of magnitude. And whatever mechanism built them took the Galactic Center, the same region we have been examining through every lens available, from radio waves to gamma rays, from the orbit of S2 to the polarization of Andy's object, and turned it into something that reshapes the architecture of the galaxy itself. The quiet center has a violent past written into the sky above and below it. The answer about when it happened and what caused it leads directly into one of the loudest unsettled arguments in modern astronomy. two origin scenarios for the Fermi Bubbles are currently competing for scientific consensus, and they have been doing so with genuine intensity since 2010. Neither has been ruled out, neither has fully won, and the stakes of the debate go considerably beyond academic priority. The first scenario centers on Sagittarius A star itself. The hypothesis holds that approximately 3.5 to 6 million years ago, the black hole entered an active accretion phase, consuming a significant quantity of infouling material, possibly a dense molecular cloud or a cluster of stars that wandered too close. As the material spiraled inward through the accretion disk, it released energy at a rate orders of magnitude higher than the present quiescent state. Some fraction of that energy coupled to the surrounding gas and drove a powerful outflow, a combination of a collimated relativistic jet and a wider angle wind of hot plasma that punched out of the galactic plane and inflated the bubble structures that Fermi later detected. Under this scenario, SGR A star was briefly doing what active galactic nuclei do routinely, just on a shorter timescale and at a lower peak luminosity than the most extreme quasars. The Galactic Center had a Seyfert Galaxy episode. It lit up, blew its bubbles, and then went quiet again. The second scenario redistributes the energy source away from the black hole entirely. The Galactic Center contains one of the most intense star-forming environments in the Milky Way, a region capable of producing massive stars at rates far above the galactic average, clustered in compact regions where stellar densities reach extraordinary values. A starburst episode, a period of exceptionally rapid Schenker-concentrated star formation, would generate massive stars that live fast and die violently. Their stellar winds during their short lives, combined with the sequential supernova explosions as they exhaust their fuel and collapse, would inject enormous amounts of thermal energy and momentum into the surrounding interstellar medium over timescales of a few million years. The accumulated mechanical energy from thousands of supernovae concentrated in the central few hundred light years could drive a large-scale outflow capable of inflating the bubble structures without requiring SGR A star to have done anything unusual at all. Both mechanisms are physically plausible. Both have advocates who have published detailed modeling work, showing their preferred scenario can reproduce the observed properties of the Fermi bubbles within reasonable parameter ranges. The debate has been ongoing for 15 years without decisive resolution. Then, in 2020, two separate observational results arrived that significantly sharpened the picture. The first came from a combination of data from the Hubble Space Telescope and the XMM Newton X-ray Observatory. Astronomers studying the Magellanic Stream, a long ribbon of gas pulled from the large and small Magellanic Clouds that arcs across the southern sky, found evidence of an ionization cone, a region of enhanced ionization consistent with having been illuminated by an intense burst of radiation from the direction of the Galactic Center. The geometry and the ionization state of the gas in this cone were analyzed in detail. The conclusion was striking. The ionization pattern is consistent with a flare from SGR A star occurring approximately 3.5 million years ago, with a total energy output on the order of 10 to the power of 56 ergs. 10 to the power of 56 ergs. To contextualize that number, our Sun, over its entire expected 10 billion year lifespan, will radiate a total energy of approximately 1.2 times 10 to the power of 51 ergs. The SGR A star event, implied by the Magellanic Stream ionization cone, released roughly 100,000 times the total lifetime energy output of our Sun in a single episode, over a period estimated at perhaps a few 100,000 years. The Large Magellanic Cloud, which sits approximately 160,000 light-years from the Milky Way, had its facing gas illuminated and ionized by that outburst from 200,000 light-years away. 3.5 million years ago, our ancestors Australopithecus afarensis, walking upright across the East African landscape, making simple tools. Living in small groups, had no concept of galaxies, no language to describe what they could not see, and absolutely no awareness that the center of their own galaxy was at that moment generating a beam of ionizing radiation powerful enough to reach a satellite galaxy 160,000 light-years away and leave a detectable chemical mark on its gas. They walked in the dark beneath a sky whose most dramatic event was playing out silently far above them. The entire drama, 10 to the power of 56 ergs of energy, ionization cones stretching across intergalactic distances, bubbles of hot plasma inflating to 25,000 light-years in height, was invisible to every living thing on Earth. The second result in 2020 came from the A Rosita All-Sky Survey, conducted by the Spectrum Röntgen Gamma Space Telescope. In the X-ray data, a team led by Peter Pradale identified two enormous structures extending above and below the galactic plane, now called the Rosita Bubbles. They are larger than the Fermi Bubbles, reaching approximately 45,000 light-years from the galactic plane in each direction, with sharp outer edges and interior temperatures estimated in the range of tens of millions of degrees. The A Rosita Bubbles appear to be the outer shock fronts driven by the same energy injection event that inflated the inner Fermi Bubbles, and their properties, size, temperature, edge sharpness, are consistent with a powerful outburst from the Galactic Center occurring a few million years ago. Two independent observational programs, two independent datasets, both pointing to the same conclusion: SGR A star, or the central starburst, or some combination of both, unleashed a catastrophic energy release a few million years ago that structured the entire region above and below the Milky Way's disk on scales of tens of thousands of light-years. Now for the part that cannot be comfortably set aside. SGR A star is not dead. It is accreting right now, at a low but measurable rate. X-ray telescopes have documented flares, some of them significant brightenings of a factor of a few hundred in X-ray luminosity occurring multiple times per year as clumps of gas and, occasionally, larger objects fall toward the event horizon. The gas cloud G2, discussed in Part 5, delivered some material to the accretion environment during its 2014 periapsis passage, even as the main body survived. The stellar winds from the dense S star cluster continuously rain material onto the central parsec. The fuel for accretion is present. The mechanism is running. The rate is low today, but 3.5 million years ago, it apparently was not. Nothing in the physics of black hole accretion guarantees that the rate stays low. The transition from quiescence to activity is driven by the availability of infalling material. If a sufficiently large molecular cloud, or a dense cluster of stars, were gravitationally perturbed onto an orbit that brought it into the central parsec, the resulting increase in accretion rate could trigger a new active phase. The conditions for such perturbations exist in the Galactic Center today exactly as they existed 3.5 million years ago. If something equivalent to the event implied by the Magellanic Stream ionization cone were to occur again right now, today the light travel time from the Galactic Center to Earth is 25,800 years. The ionizing radiation would travel at the speed of light. The warning would arrive at the same moment as the event itself, indistinguishable from it. By the time any detection system on Earth registered the first photons of a new galactic center flare, those photons would have already been traveling for 25,800 years. We would, technically, have 25,800 years to prepare, starting from 25,800 years ago. The preparation window closed before agriculture existed. The universe's version of advance notice is generous in light years and completely useless in practical terms. But all of it, the bubbles, the wall, the G objects, the gamma rays, these are only fragments of a picture far larger than any single piece suggests. Sagittarius A star should not be understood as a point, not as a single isolated object sitting at the center of the Milky Way, doing its own thing independently of everything around it. What the previous 13 parts have collectively described is not a black hole and a collection of unrelated curiosities. It is an ecosystem, a physically coupled, mutually interacting system of components that regulate, feed, and transform one another on timescales, ranging from hours to millions of years. The components of that ecosystem, a 4 million solar mass black hole at the center, a population of paradoxically young stars in tight orbits around it, including S2 racing at 2.55% of the speed of light. 6G objects, merged stellar products wrapped in gas envelopes, completing their long elliptical orbits and periodically sweeping through periapsis without being consumed. A magnetic field orders of magnitude stronger than the galactic average, coherently structured over hundreds of light years. A cosmic ray barrier maintained by that field and by galactic winds, keeping the interior of the central molecular zone energetically distinct from the outer disk. A gamma ray excess glowing symmetrically from the center. Disputed between 100,000 millisecond pulsars and annihilating dark matter particles. And a periodic radio transient whose near-complete polarization points to a magnetic environment of extraordinary organization. And 2 sets of bubbles, the Fermi Bubbles at 25,000 light-years and the Rosetta bubbles at 45,000 light-years, recording in the structure of the galactic halo the violence of a past eruption that ionized gas in a satellite galaxy 200,000 light-years away. Taken individually, each of these is a fascinating anomaly. Taken together, they form a system with internal logic, not random weirdness, but interconnected processes that generate and respond to each other continuously. Trace the chain. Energy from SGR A star's accretion and from the surrounding stellar population drives a galactic wind outward from the central region. That wind, carrying the coherently organized magnetic field of the CMZ with it as it flows, maintains the pressure gradient that partially excludes cosmic rays from the central molecular zone. The reduced cosmic ray flux inside the CMZ contributes to maintaining the thermal and chemical conditions of the dense molecular clouds there, the very clouds that, when dense and cold enough, collapse to form new stars. Those new stars, forming in the extreme gravitational environment near the black hole, either migrated inward through multi-body gravitational interactions or form through mechanisms not yet fully understood, producing the paradoxically young S-star population. Among those stars, and among the broader stellar population of the central parsec binary systems interact, merge under the tidal influence of SGR A star, and produce the G objects, merged stellar products that spiral through their elongated orbits and eventually approach periapsis, delivering some material to the accretion environment and surviving to continue their cycles. The accretion of that material, however modest, feeds the energy output that maintains the galactic wind, that maintains the cosmic ray barrier, that protects the molecular clouds, that form the stars, that produce the G objects. The wheel turns. This is not a metaphor imposed on unrelated observations. Each link in that chain has observational support. The galactic wind is detected. The cosmic ray deficit in the CMZ is measured. The star formation in the CMZ is documented. The G objects are directly imaged. Their orbital dynamics near SGR A star are tracked. The feedback from accretion to outflow is a well-established physical process in active galactic nuclei, operating here at lower intensity, but by the same mechanism. What we lack is a model that holds all of it simultaneously. Running a full magnetohydrodynamic simulation of the Galactic Center ecosystem, one that captures magnetic field structure at milligauss resolution, cosmic ray transport through the CMZ boundary, stellar orbital dynamics on parsec scales, molecular cloud chemistry and star formation, G-object evolution, and accretion feedback from SGR A star across timescales of millions of years, requires a computational framework that does not exist yet. The physical processes span roughly 12 orders of magnitude in spatial scale from the event horizon of SGR A star at roughly 12 million kilometers up to the Fermi Bubbles at 25,000 light-years. No single simulation grid can resolve both ends of that range simultaneously with current technology. Researchers work on pieces simulating the accretion environment without the bubble dynamics, or modeling the bubble inflation without the detailed microphysics of the CMZ. Each piece is valuable. None of them is the whole picture. Think about what that limitation actually means for everything we have discussed. The global weather system of Earth is driven by differential solar heating, ocean circulation, topographic effects, atmospheric chemistry, and the Coriolis effect from Earth's rotation, all interacting simultaneously across scales from millimeters to thousands of kilometers. Forecasting weather more than about 2 weeks out remains beyond reliable capability despite decades of satellite data, supercomputer modeling, and continuous real-time measurement from millions of stations worldwide. The system is simply too coupled, too nonlinear, too sensitive to initial conditions for long-range deterministic prediction. Now consider trying to forecast the behavior of the Galactic Center ecosystem with approximately 10 measurement points, 10 telescopes, 10 frequency bands, snapshots taken over a few decades at most applied to processes that operate over millions of years and interact across 25,000 light-years of intervening space. We are not doing global weather forecasting. We are trying to predict global weather from temperature readings at 10 cities, taken over a period of 30 seconds. This reframing is not defeatist. It is clarifying. What we label as anomalies, the paradox of youth, the G-object survivals, the cosmic ray deficit, the gamma ray excess, the aperiodic radio transient. These might not be anomalies at all. They might be the normal operating signatures of a coupled physical ecosystem that we are reading in fragments, out of temporal context, without the full model that would make each piece fit naturally into the whole. In a sufficiently complex interacting system, every subsystem looks strange when observed in isolation. The immune system, examined without knowledge of pathogens, looks like the body attacking itself. The Galactic Center ecosystem, examined without the unified model we do not yet have, looks like a collection of contradictions. What is genuinely dangerous, not in an existential threat sense, but in an epistemological sense, is the possibility that the most significant processes happening in the Galactic Center right now are completely invisible to our current instruments. The Fermi Bubbles were there all along, fully formed, waiting in the data before anyone noticed them. Andy's object had presumably been flashing on and off for years before the right survey caught it. The E Rosita bubbles required a new all-sky X-ray survey to become apparent. Each generation of instruments has revealed a layer of activity that the previous generation could not see. What is the current generation missing? And the most dangerous thing is not what we have already seen. It is what is happening right now that no instrument we currently have can detect. The Square Kilometer Array is the largest radio telescope ever built by human civilization. Not a single dish, but an array thousands of individual antennas distributed across 2 sites, one in the Karoo Desert of South Africa and one in the Murchison region of Western Australia, linked together through high-speed fiber and processed by supercomputers capable of handling data volumes that exceed the global internet traffic of the early 2000s. The collecting area. When Phase 1 reaches completion in the mid-2000 and 2010s, will be measured in square kilometers, hence the name. The angular resolution and sensitivity this array achieves will exceed anything currently operating in radio astronomy by a significant margin. for the Galactic Center specifically. The square kilometer array represents a qualitative leap rather than a quantitative one. The magnetic field structure of the central molecular zone, the milligauss strength, coherently organized field that deflects cosmic rays and imprints near-complete polarization onto the emission from objects like Andy's object, has been mapped only coarsely with existing instruments. Because the angular resolution needed to trace the fine-scale geometry of those field lines requires baselines and sensitivity that no current array provides at the relevant frequencies. The square kilometer array will map the polarization of radio sources across the galactic center. With sufficient resolution to trace magnetic field structure on scales down to individual molecular cloud complexes, revealing how the field is organized at the level where cosmic ray deflection actually occurs, rather than inferring it from bulk averages. Beyond the magnetic field mapping, the square kilometer array will conduct a continuous transient survey of the radio sky at sensitivity levels that dwarf previous monitoring programs. Andy's object, Gleam X J16275-5.5-52350.3, was found essentially by accident in data that was not specifically designed to hunt for ultra-long period radio transients. The square kilometer array will be running purpose-built transient detection pipelines across the full sky, including the Galactic Center, continuously. If the object belongs to a class with dozens or hundreds of members hiding below current detection thresholds, the square kilometer array will find them. If it is genuinely singular, one of a kind, an object without counterparts, the square kilometer array will establish that too, which is its own kind of answer. The Vera Rubin Observatory, operating from Cerro Pachon in Chile since 2024, is doing something different, but complementary. Its legacy survey of space and time, LSST, will image the entire accessible southern sky repeatedly, building a decade-long time domain dataset of extraordinary depth. Every variable source, every transient, every object that changes brightness or position between visits gets flagged and characterized automatically. For the Galactic Center and surrounding regions, this continuous cadence will produce a catalog of variable sources, orders of magnitude larger than anything previously assembled. New classes of radio transients often have optical or near-infrared counterparts, faint, variable, previously uncatalogued, that Rubin will detect even when the radio signal itself requires a dedicated radio telescope to confirm. The combination of Rubin's optical time domain sensitivity with the square kilometer array's radio coverage creates a multi-wavelength monitoring system for the Galactic Center region that simply has no predecessor. Gravity Plus is the upgraded version of the Gravity Interferometric Instrument installed at the Very Large Telescope Interferometer operated by the European Southern Observatory in Chile. The original gravity instrument was responsible for the definitive measurement of Sagittarius A star's mass through stellar orbital tracking, and for the 2018 observation of S2's gravitational redshift that provided the first direct confirmation of general relativity near a supermassive black hole. Gravity Plus extends the instrument's capabilities, wider sky coverage, improved sensitivity through laser guide star adaptive optics on all 4 unit telescopes of the VLTI simultaneously, and the ability to observe fainter stars closer to SGR A star than was previously possible. What Gravity Plus enables is a more precise, more extended orbital monitoring campaign for the S star cluster. S2 completed its last periapsis in 2018. Its next closest approach occurs around 2034. With Gravity Plus operational, that periapsis passage will be observed with instrumentation roughly 10 times more sensitive than what captured the 2018 event. The additional precision will allow detection of higher-order relativistic effects, not just gravitational redshift and the first-order Schwarzschild precession already measured, but potentially the frame-dragging precession caused by SGR A star's spin which encodes information about the black hole's angular momentum. Measuring SGR A star's spin through stellar orbital dynamics would add a fundamental parameter to our characterization of the object, a parameter that current observations cannot access. It would also allow stronger tests of whether the space-time geometry near SGR A star matches general relativity's predictions in detail, or whether deviations suggest modifications to gravity that current theory does not anticipate. The Cherenkov Telescope Array CTA is the next-generation ground-based gamma-ray observatory, currently under construction at two sites, La Palma in the Canary Islands for the Northern Array, and Paranal in Chile for the Southern Array. When complete, CTA will consist of roughly 170 individual telescopes of 3 different sizes, designed to detect the faint Cherenkov light flashes produced when very high-energy gamma rays interact with Earth's atmosphere. Its sensitivity at energies between roughly 20 giga-electronvolts and 300 tera-electronvolts will be approximately 10 times greater than any current gamma-ray instrument in that energy range. For the Fermi Galactic Center excess, this sensitivity gain is potentially decisive. The unresolved point source hypothesis, 100,000 millisecond pulsars summing to produce the observed glow, predicts that above certain energy thresholds, the angular structure of the emission should reveal the statistical signature of a discrete source population, even if individual pulsars cannot be resolved. CTA has sufficient sensitivity to test this prediction directly. If the excess is truly a collection of discrete sources, CTA's data should show spatial and spectral structure inconsistent with a smooth diffuse component. If it is genuinely diffuse, consistent with dark matter annihilation, producing gamma rays uniformly from within the dark matter. Halo density profile, CTA's data, will be consistent with that smoothness at a level that current instruments cannot confirm. The dark matter versus pulsar debate that has occupied a significant fraction of high-energy astrophysics for 15 years may have a resolution within the lifetime of people currently reading about it. These 4 instruments, the Square Kilometer Array, the Vera Rubin Observatory, Gravity Plus, and the Cherenkov Telescope Array, represent different windows onto the same system, scheduled to reach their full operating capabilities within a decade of each other. They will not work independently. The science they produce will cross-inform radiopolarization maps from the Square Kilometer Array will constrain the models of cosmic ray transport tested by CTA's measurements of the Galactic Center emission. Gravity Plus orbital data will refine the mass model of SGR A star used in dark matter annihilation calculations. Rubin's transient detections will identify optical counterparts for Square Kilometer Array radio sources, triggering follow-up observations that turn discoveries into classifications. But there is one thing none of these instruments can provide, and no budget allocation, no engineering breakthrough, no international collaboration agreement can supply it: patience. The phenomena playing out in the Galactic Center operate on timescales that mock human ambition. The Fermi Bubbles took millions of years to inflate. The G objects complete their orbital cycles over decades to centuries. The magnetic field structure of the CMZ evolves over timescales of tens of thousands of years at minimum. The next periapsis of a G object that comes close enough to SGR A star to stress test the survival hypothesis will happen on a schedule the galaxy keeps. Not one we set. The next major accretion event that could trigger a new active phase in SGR A star, if one is coming, will arrive when the infalling material arrives, indifferent to the tenure schedules of the astronomers waiting to observe it. We can build instruments faster. We cannot make the universe move faster. Every telescope we construct is being aimed not toward peace of mind, but toward clarity about what is watching us back from the centers of the only galaxy we have ever called home. That is not a comfortable motivation. It is an honest one. the Galactic Center doesn't care that we find it difficult to understand. It runs on its own schedule, couples its own systems, generates its own structures, and has been doing so for billions of years before the first human eye looked up at a dark sky and wondered what the bright band overhead might be. We are building better eyes. The universe is not adjusting its behavior to accommodate our observing programs. And when you look long enough, deeply enough, the boundary between astronomy and philosophy begins to dissolve. From 25,800 light years away, using radio waves that cut through dust, using an Earth-sized telescope network that required atomic clock synchronization across 7 continents, using infrared instruments that see through the molecular fog our ancestors never knew existed. We looked directly into the heart of our own galaxy and took its portrait for the first time. That is not a small thing. That is extraordinary. But every mystery examined in this story remains open. The map was wrong and is still being redrawn. Stars orbit where stars cannot form, and no one has proven how they got there. Objects survived what should have destroyed them, and the explanation is still a hypothesis. An invisible wall holds back cosmic rays through mechanisms we cannot fully simulate. A gamma-ray glow burns with perfect symmetry and refuses to confess its source. A radio signal blinks without rhythm or reason, carrying the fingerprint of a magnetic environment that fits no existing category. And above and below the galactic plane, 2 sets of enormous bubbles preserve the record of a violence so extreme it ionized gas in a satellite galaxy 200,000 light-years away, while the object responsible sits quietly at the center, accreting slowly, saying nothing. Not one of these is resolved. That is not failure. That is the actual shape of knowledge at its frontier, ragged, unfinished, and far more interesting than any clean answer would be. The Galactic Center is not a threat to be feared or a problem waiting for a solution. It is an invitation to stand at the edge of what human understanding has reached. Look into the complexity that the universe actually contains, and recognize that our existence here on a small planet, on an outer arm, in a galaxy whose center is quietly rewriting the rules of physics is a rare privilege. Scientists are not panicking because they see danger. They are unsettled because they are beginning to understand just how much they do not yet understand. And that, precisely, is where science actually begins.